we move on to the first plenary session of the Saga 7 2023, which is on the climate change and the Arctic sea ice, lessons learned and future strategies, for which I have the proud privilege in inviting Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology, Pune. He specializes in climate modeling and studies relating to climate change, the Asian monsoon and the water cycle. Under his leadership, the CCCR at IITM Pune developed the first Earth System Model ESM from India and contributed to the Coupled Modeling Intercomparison Project Phase 6 and the IPCC 6th Assessment Report. He is member of the Joint Scientific Committee, JSC, the World Climate Research Program, World Meteorological Organization, and his team from CCCR IITM published the first National Climate Change Assessment Report of Ministry of Earth Sciences in 2020. So, ladies and gentlemen, please welcome Dr. R. Krishnan for his plenary address presentation on climate change and the Arctic sea ice, lessons learned and future strategies.
So this presentation is on climate change and the Arctic sea ice, the lessons that we have learned and future strategies. I would like to specially acknowledge and thank my colleagues Dr. Swapna and Sandeep from the Center for Climate Change who have made many of these model experiments which I will be sharing with you. And basically this will be about the science of climate change, which was described today morning by many of our eminent delegates. So climate change is already happening, and it's happening at a very fast rate. And especially the Arctic region, the temperatures have increased. Recent records show that warming is almost 4 times faster in the Arctic compared to rest of the globe. And its impact on the ice, the cryosphere, is already happening, and the future projections are quite alarming, I would say. So I will be presenting some of the results from the what we have seen and the IPCC AR6 assessment and the special report that was also mentioned in the morning talk, and what are the ways forward, what are our future strategies. I will be touching upon those issues. So I'll quickly move on. So we know human influence is already influencing the climate, the increasing greenhouse gases. The temperature in 2022 was almost 1.2 degrees warmer than the pre-industrial climate, and we know that it is mainly the greenhouse gases that have contributed to this rapid warming, and this is all very well known now. But when we look at the spatial pattern of warming, surface temperature increase, it is not uniform. This is from the IPCC report again. Maximum warming in the polar Arctic region. What we see in the top left panel is from the observations, and the models are almost able to get this pattern of warming in the Arctic. And but of course there are small differences that you might see in the ocean. At North Atlantic Ocean there is a slight cooling which the models tend to underestimate, and also the hotspots of warming in the Arctic are also not adequately captured. But apart those finer details, the broad pattern of warming in the Arctic, the models are able to capture, the CMIP6 models. And when we look at the future projections, with additional increase in the global warming, the Arctic warming is also going to increase, and with that the precipitation is also projected to increase in the Arctic and many regions in the tropics, including the monsoon. And but when we look at the temperature increase in the since 1979, last 40 plus years, the rate of warming, a recent study shows that it is almost 4 times warming compared to the rest of the globe, faster rate of warming. And in fact, after the 2000, the Arctic amplification has been recognized. The Cohen et al. Study was an important paper, but now new estimates are saying that the rate of warming is much higher, and this is leading to increased melt of ice, and also the ice sheets like the Greenland ice sheet, where extreme melting was observed in 2019 and also 2021, and these have enormous consequences on the atmospheric circulation, also on the ocean. This is a very important paper that came in the 2022 in oceanography, the changing Arctic sea ice cover. So, if you see the trends in the Arctic sea ice cover in March, the decline is something like 2.6 percentage per decade. But during September, that is a month when the Arctic sea ice is minimum climatologically, the rate of decrease is much faster, stronger. It's about 12.7% per decade. And also when we look at the distribution, month-wise distribution in spatially from 1900 to 2020, you can see that the September, October, during that time, the decline in the Arctic ice is very prominent after 2000. So in the last 20 years, the decline has been very pronounced. And from the IPCC assessment, we also see that the Arctic sea ice area decreased, the same pattern that we see, although from the 1980s there is a decrease. From 2000 onwards, the last two decades, more than 2 decades, the decline, especially in the September months, is very prominently seen. And the models are also able to capture this. You have the observations and the model, and then the future projection, one of the SSP 245, that's a kind of median emission scenario into the future. The sea ice concentration both for the month of March and for the September is projected to decrease in the future. And in fact, they don't give the concentration itself. What is the metric is the number of models above 15% of the sea ice concentration. That's a kind of a threshold. And you can see most of the models are very few models are showing that a large part of the Arctic it will decrease above. It will be about 15%. That's shown in green color in the bottommost panel. And so the models are also capturing there. This was also came out in the morning talk that there will be a time in the by 2050s in all the scenarios, considered scenarios of the AR6, September Arctic ice there could be practically ice free. And so unless only in the SSP 119 and 126, which are the low emission scenarios, the Arctic can be saved from the Arctic free ice condition can be saved. Otherwise, this situation is going to happen. So these have grave consequences. So what does that mean, and what we are doing at our center at the Climate Change Center at IITM? So this was the first model, Earth system model from India that was developed, the IITM Earth system model. My colleagues, Dr. Swapna was leading this activity. And one of the problems, and this model contributed to the AR6 assessment. And one of the problems, the version 1 model that we developed, ESM1, in 2014, one of the problem was the Arctic sea ice was terribly underestimated. And this led to major problems in having a radiatively balanced system. So any climate model should have a radiation balance before subjecting it to increasing concentration of greenhouse gases. Unfortunately, the first version of the model, it was suffering from this problem, and we realized that this was one of the major issues was with the Arctic sea ice, and which was rectified in the second version, which is shown which was improved in the version 2. And you can see the monthly, and this is the model. We had a radiatively balanced system which went into the CMIP 6 projections. And the bottom panel shows the sea ice month-wise sea ice distribution from the sea ice extent from the model and from the observations. Although we have improved the sea ice distribution, still it is being, even the version 2, the July, August and September sea ice, still it is underestimated compared to the observations. We need to work on that, and future projections is shown in the right panel. So in the future, as the temperature increases with increase in greenhouse gases, Arctic sea ice is projected to decrease. That is very clearly coming out. So what are the consequences of this melting Arctic meltdown? One thing, it can lead to extreme weather, which was nicely brought out in today's morning's presentation. Basically in the Arctic, we have what is known as a polar vortex. Because when we look at the atmospheric general circulation, in the tropics we have this Hadley's type of circulation, Hadley cell, and we have the easterly trade winds. In the mid-latitude, the Hadley cell breaks into the form of baroclinic waves, and further north we have a polar cell. So as the temperature increases and the Arctic ice melts, this vortex can break down, and it can, so the jet stream, in normal conditions we have a very strong polar jet stream, and that polar jet stream can weaken once the Arctic ice melts, because of the changes in the temperature gradient between the mid-latitude and the polar region, and it can produce meanders in the jet stream, the polar jet stream, which can also influence the mid-latitude jet stream. And these changes in the mid-latitude jet stream can lead to weather extremes like heat waves, like the Russian heat wave in 2010. Many studies have shown that, and also extreme precipitation. For example, the 2010, there are some studies which have attributed to 2010 Pakistan floods and several other weather extremes, precipitation and flood extremes. And this morning, our secretary, Dr. Ravichandran, was talking about this paper about the Arctic sea ice connection with the Indian monsoon and the extremes during the month of September. This was a paper by Saurav Chatterjee, Ravichandran et al. And they showed that there is out of phase connection between the sea ice cover, Arctic sea ice, especially in the Kara Sea, and the heavy precipitation in September in the Indian region. And there is also a interdecadal relationships between these two quantities. How this connection happens is through a pattern of atmospheric teleconnection. That's what they describe. Now, this is a study by our colleague Dr. Sandeep, which is a very interesting piece of work. So, we are looking at the extreme precipitation over South Asia, and the left panel shows the extreme rain. It is going from top to bottom, 50 to 350 events, and in the x-axis we have the time axis, and you can see a clear increase in the heavy precipitation events over the South Asian region. And when we see its relationship with the Arctic sea ice, we see a nice out of phase connection, and the spatial pattern of the correlation between the extreme rainfall and sea ice also see that many portions in the Arctic region, they have a significantly negative correlation coefficient. So we thought of doing a model experiment with the IIT MESM by imposing sea ice anomalies without changing the greenhouse gas concentrations. Just try to understand what is the effect of changing the sea ice in the Arctic, how does it influence the circulation patterns. So what we did, this is a paper by Clara Dezer, where she basically constrained the sea ice concentration in terms of the long wave radiative forcing. The long wave radiative forcing is the one typically due to the greenhouse gases. It tries to increase the downwelling radiation due to the absorption of the terrestrial long wave infrared radiation from the earth and warms the planet. And when you impose long wave radiation anomaly in the Arctic region of different magnitudes, we have 5 watts per meter squared, 20 watts per meter squared, 50 watts per meter squared. So gradually the long wave radiative forcing is increased in the model, and this leads to a corresponding change in the sea ice concentration in the Arctic. And when this experiment was performed, so as you increase the magnitude of the radiative forcing, long wave radiative forcing, the sea ice decline also increases, the extent of the sea ice decrease. And what we find in the simulation is that you can see the meanders, when you have a very smaller magnitude of radiative forcing, 5 watts per meter squared, you still see a stronger polar vortex. But as the radiative forcing increases in the magnitude and the sea ice declines, you can start seeing meandering. This is a 200 millibar atmospheric circulation, and we also see, and we want to understand what is its connection with the Indian monsoon, because in the upper troposphere, this is typically 200 millibar, the monsoon convection is there going on, and we have a strong anticyclone. So we are trying to understand what is the interaction between these mid-latitude baroclinic waves and the Indian monsoon convection and the deep circulation, upper tropospheric circulation. And when we look at these anomalies, what we see is, as the radiative forcing is increased, the blocking, the Arctic region, we have a typical blocking, and the strength of the blocking becomes stronger and stronger, and you have this very deep meridionally extending waves, wave pattern that is generated. And I'm not going into the details, but due to shortage of time. And when we compared the control experiment that is without this ice forcing and with the 80% watt per meter square, that's a very extreme forcing, we do see what are the changes in the extreme precipitation. We looked at the 1-day rainfall, 5-day mean rainfall, and this is a very, very preliminary analysis, and also the 95th percentage rainfall. Many parts of India, we do see that heavy precipitation tends to increase. We want to make it more focused, trying to understand whether these type of events like the Uttarakhand 2013 event, it was a very heavy precipitation event where there was also a monsoon low pressure system from the Bay of Bengal, and it interacted with this deep mid-latitude troughs, actually extending right from the polar regions, triggering this huge rainfall in the Himalayan region. So we want to focus on those type of events from this model experiments. What is the Arctic sea ice going to do to these type of events? That work is in still progress. So one of the effects is through the atmospheric dynamics, Arctic sea ice can influence the regional monsoons through the teleconnection patterns. The other is it can also influence the ocean circulation, because in the North Atlantic, typically the water is cold and it's also salty, so the density is very high. And whereas in the lower latitudes, you have the water is warm and also fresh. So you have a density gradient, and Henry Stommel recognized this long back that once you have this density gradient, so it can drive these circulations known as thermohaline circulation. And then it was conceived that there is a global conveyor belt. And in fact, one of the early studies of Manabe and Stauffer in 1990, they showed that if you introduce more fresh water in the North Atlantic due to the melting of the sea ice, so you can freshen, and this leads to weakening of the thermohaline circulation. Now in the literature, this THC is known as the AMOC, the Atlantic Meridional Overturning Circulation. So these on the longer time scales, the question is, with the melting of the Arctic sea ice, the question is what will happen to the Gulf Stream. So the IPCC assessment, will it shut down? Will it totally weaken? So the assessment is that it will definitely weaken. It is projected in the future that the Gulf Stream can weaken, but it will not totally cease. It will not shut down. And in fact, many of the CMIP-6 models with increasing GHG forcing, a weakening of the AMOC is projected. And so in fact, we had, as I mentioned in my earlier slide, that in the version 1 of the IITM ESM, the Arctic ice was very much underestimated. And one of the consequences was due to the freshening in the North Atlantic, the salinity was very much reduced. And practically the AMOC circulation was absent in the version 1 of the model. And so when we improved the sea ice concentration, we improved the thermohaline circulation, the AMOC, in the version 2. So there are very serious implications of the Arctic ice even on the ocean circulation. And this was an important paper by Sandeep, our group, on changes in the Atlantic meridional overturning circulation. It can also have impacts on the monsoon. So we did these experiments by forcing freshwater and heat water fluxes in the North Atlantic. We introduced through a set of experiments, and we wanted to understand what is its impact on the AMOC and the monsoon. The result is that as we introduce more heat and freshwater fluxes in the North Atlantic due to the melting, the AMOC definitely weakens, and also it tends to alter the tropospheric temperature patterns, and it tends to weaken the Indian monsoon, both the circulation and precipitation. However, as with the global warming, as the temperature increases in the lower latitudes and there is more evaporation from the oceans, the water vapor content also increases. So there is a kind of compensatory effect due to the increase of water vapor in the atmosphere due to warming. The thermodynamical response tries to compensate the precipitation decrease. So we try to get an increased precipitation because of the greenhouse gas warming. But only if you take the effect of the freshening of the North Atlantic, it tries to weaken the circulation and reduce the precipitation. I'm not going into the details. Finally, the other effect is the Greenland ice sheet is melting, and many of the glaciers are melting, and even the Antarctic ice sheet also, even the observation period in the last 3 decades or so, they have reported reduction, there's a negative mass balance. So the IPCC projection is that this is going to continue into the future, and this can have the melt, because you're going to add more water, into more mass into the ocean, and it has consequences on the sea level rise. So if you see the estimates for the observed period, this is from 1970 to 2014. We can see a substantial increase when you look at the global sea level budget. The melting of the Greenland and Antarctica ice sheet and various glaciers, they have almost contributed 40% to the increase of the global sea level. And with increasing temperatures in the future under the different SSP scenarios, we can see the global sea level is projected to increase by about half a meter, by more than half a meter, by at least when you look at the SSP 245 by end of this century. So the consequences globally, this is going to have big impacts. And so what are we doing? We have also developed we are trying to introduce a sea ice model. We are starting with the Greenland in the IITM Earth System model. First we are making standalone experiments, and this already significant progress has taken place. So using the IITM ESM, we provide the inputs of precipitation and temperature to the ice sheet model, and compute different outputs, the accumulation, ablation, and which are all important for the mass balance of the ice sheet. And what is the freshwater flux that comes out of that is fed into the IITM ESM. So this is being integrated. This will go into the CMIP 7 as one part of the activity of the CMIP 7. And I'm not going into the details. So in summary, it came out in the introductory talk that the cryosphere is a very important. All people on the earth depend directly or indirectly on the ocean and cryosphere. This is from the special report of the Ocean and Cryosphere, IPCC. Of course, the ocean covers 71% of the Earth's surface and contains 97% of the Earth's water. And the 10% of the Earth's land area is covered by glaciers and ice sheet. The oceans and cryosphere support unique habitats and are interconnected with other components of the climate system through global exchange of water, energy, and carbon. So with the increasing carbon dioxide, with the increasing warming levels, the cryosphere, especially the Arctic region, we are going to see major consequences. There are also various climatic feedbacks which cannot be avoided, and there is a possibility of abrupt climate change also, and irreversibility. And the Arctic sea ice will become practically ice-free during the seasonal sea ice minimum for the first time before 2050 in all the considered scenarios. However, this is not a tipping point. There is a discussion on tipping point. The Arctic sea ice is not a tipping point. This is a high confidence statement from the AR6. And so what are we doing? So the changes in the Arctic sea ice, what are its consequences on the Earth system? One is extreme weather over the mid-latitude, subtropics, and also over the Indian region, the monsoon region, through various changes in the atmospheric circulation patterns. It has consequences on the water cycle, the large-scale phenomena like the regional monsoons, ITCZ movements through changes in the ocean circulation and SST, and the melting glaciers and large ice sheets, especially the Antarctic and Greenland, have major implications for global sea level rise. So reliable projections and improved assessment of Arctic climate change, they are essential. So we need to advance capabilities in climate and earth system modeling and prediction systems, advance impact assessments, development of adaptation strategies to mitigate risk and for policy making, improve early warning systems, and more importantly, advance scientific research, academic collaborations to complement and enhance in-house R&D capabilities such as the IITM Earth System model. So with this, I want to end my talk. Thank you very much for this opportunity. Jai Hind.